Now we're going to consider what happens when the wave moves along a medium and comes to a boundary. At this point, two things can happen. The wave can be reflected or it can be transmitted. Now, if the wave comes to a fixed boundary, it's reflected, but it actually undergoes a phase change. So if we had a pulse travelling along a string, it got to this boundary and it was reflected, it would be reflected back underneath the string. If the wave is travelling along and comes to a boundary which is free to move, so for example a loop on a rod, in that case when it gets reflected from this boundary it doesn't undergo a phase change. If the pulse was travelling along the string on top of the string and it was reflected, it would travel back also on top of the string. So let's have a look at a demonstration of that now, taken from PhysClips.
At boundaries, there are usually reflections. This string is tied to an object so massive that its acceleration is negligible. As the pulse reaches the boundary, the force exerted on the string by the fixed end accelerates the peak downward. The resultant momentum takes it past equilibrium into negative displacement. So, at an immovable boundary, we say the wave is reflected with a phase change of pi. The animation shows the original pulse travelling right plus an inverted pulse travelling left. In a linear medium, we can simply add them to give the observed reflection. In this apparatus, torsional waves travel in one dimension. The displacement here is the angular displacement of these bars, and the restoring effect comes from the torsional stiffness of this steel strip. The inertia is the rotational inertia of the bars. With a fixed boundary, we again see reflection with a phase change of pi. Now we remove the clamps. The boundary is completely free. What happens at reflection this time? Here there is no restoring effect at the free boundary, so the displacement there is greater. The upwards momentum of the pulse is now transferred to the trailing edge, which in turn sends a pulse back from the boundary with a phase change of 0. The pattern we observe is the sum of the original wave plus a reflected wave with the same sign. If the boundary is neither fixed nor completely free, we see transmission at the interface as well as reflection. Here, the string and the rope have different line densities μ, but when connected, share the same tension. Going from low density to high, we see that the wave reflected at the join has a phase change of pi. So does the reflection from the fixed end. As a result, both reflections return on the left side. Going from high density to low, the wave reflected at the junction has a phase change of 0, so it returns on the right side. The reflection from the fixed end still has a phase change of pi, so the two reflections return on opposite sides. In both cases, note that the transmitted wave has no phase change.
Now, if a wave comes to a boundary, some of it may be transmitted. If it's transmitted, then it just continues going like it was before. However, the speed of the wave in that new medium may be a bit different to how it was in the first medium. If waves move to a more dense medium, a kind of heavier medium, then they start travelling slower and their wavelength actually gets a bit shorter as well. If a wave goes to a less dense medium, so like it's travelling from a really fat rope and it goes into a really skinny rope, it then starts to travel faster. So often you get a combination of reflection and transmission at a boundary.
So with that in mind, watch this again. See how on the left-hand side, when it travels to the more dense medium, the wave slows down and the wavelength actually decreases. On the right-hand side, when it travels to a less dense medium, the wave actually speeds up and the wavelength gets a little bit longer.
So we've seen that as a wave moves from one medium to another, its velocity will change. If it goes to a more dense medium, it will slow down, And because of our equation v is equal to f lambda, when it moves from one medium to another, the frequency doesn't actually change. So if the velocity decreases, lambda, the wavelength, also has to decrease. So this is why waves get more compressed when they move into a more dense medium. If it moves into a less dense medium, then it travels faster and the wavelength spreads out.